So thank you very much for the kind invitation. I'm really glad to be here today to discuss and to present our results about the optical approach to Spintronics and Magnonics. And I would like to start by directly state our scientific goal. We aim at the manipulation of the macroscopic magnetic order on the ultrafast time scale. The reason why we work so hard towards this goal is clear if you look at the different time scale of spin dynamics from different perspectives. I would like to start discussing briefly the nanosecond regime. When you discuss this regime of spin dynamics, you can rely on thermodynamics, simply because you can use the concepts of equilibrium and adiabaticity. So this framework is really well established. For this reason, this regime of spin dynamics is already currently employed in nowadays technology. But when you start to look at shorter time scales, picosecond and femtoseconds, there is no well-established framework that we can use. We are trying to build up this framework in a tight collaboration between experiments and efforts of theory. And what we are finding out, interestingly, is that in this fast regime of spin dynamics, in this ultra-fast regime of spin dynamics, a very natural interplay between classical and quantum physics emerges. Today, I will show you mainly two experiments, one that can be almost entirely described in terms of classical physics, and another one that turned out to be a full quantum mechanical process. Of course, if you want to measure this kind of dynamics, you need the proper tool. And one of the few tools is a femtosecond optical laser pulse. So today, I will describe all optical experiments. Clearly, this research area might become of some relevance in the conceiving of next generation device for information technology, provided that we learn how to control the magnetic order on the ultra-fast time scale in a controlled way, and also really important, to avoid as much as possible heating and energy dissipation. So after this very broad introduction, I believe that we can summarize the whole goal and framework of this research field with only three words: femto, nano, and spin. And if you think about ultrafast spin dynamics, the first phenomenon that usually comes to mind is the ultrafast demagnetization. In 1996, the group led by Professor Bigot demonstrated that a 100 femtosecond optical laser pulse demagnetizes a sample of nickel in less than 1 picosecond. A second breakthrough experiment was reported 10 years ago in Nijmegen, where my colleagues showed that a single laser pulse can reverse the magnetization of an alloy of gadolinium iron cobalt. This process is fully deterministic, which means that one laser pulse switches the magnetization and the following one switches it back. And you can go on in this way as long as you want. Both of these experiments were performed on metallic samples. And when you shine light on a metal, you do excite the free electrons. The hot electrons give rise to a series of interactions with the lattice and the spins, triggering very complicated pathways of transfer of energy and angular momentum, which in the end results in the demagnetization and all optical switching. But these processes are intrinsically very complicated. So complicated that even nowadays, the microscopic mechanisms underlying demagnetization and optical switching are still under debate. I'm showing this not because I aim at discussing metals today, but just because this complicated scenario inspired us by triggering a very specific scientific question. Suppose that we can simplify the problem by exciting spins and only spins on a time scale of 100 femtoseconds or even less. In that case, what would be the resulting spin dynamics? Well, if you want to address this question, you have to choose the proper material. And the proper material is a dielectric antiferromagnet. Of course, we want to work with insulators, because in insulators there are no free electrons. And in this way, we avoid all those interactions triggered by the hot electrons that we are trying to avoid to simplify the problem. Then antiferromagnets recently have attracted a lot of interest in the Spintronics community because they are believed to be candidate material for next generation technologies, mainly because of the absence of magnetization and so stray field. But for us, the goal is going fast. And antiferromagnets have intrinsically faster spin dynamics than ferromagnets. This is a general statement. But in particular, today I will show you that when you use light to excite spin dynamics, the light-induced spin dynamics in an antiferromagnet is dramatically faster than in a ferromagnet. And I will come back to this point in a while. When I use the word antiferromagnet today, I do refer to the easiest possible antiferromagnetic structure, two collinear sublattices. No DMI, no spin texture, no skyrmions, just two collinear sublattices, which we can describe with the Heisenberg model. So if you have an Heisenberg antiferromagnet and you would like to characterize the response, dynamic response of spins, what you can do is measure or calculate the dispersion of the magnons. So I'm showing here the Heisenberg Hamiltonian, with assuming a single axis anisotropy. You can diagonalize it and calculate the dispersion of the magnons following textbook procedure. Doing so results in this curve. This is the general dispersion curve for antiferromagnets. And I would like to focus your attention in the beginning on what happens in the center of the Brillouin zone. Because we use light to excite magnons. And on this scale of wave vector, the wave vector of light is basically 0. So it is well known that light can couple to this magnon. And roughly 10 years ago, it was demonstrated that light can couple to these magnons even on the ultrafast time scale. This was shown by Alexei Kimmel in these breakthrough experiments published in 2005, when he excites coherent oscillations of the magnetization due to magnons using ultra-short laser pulses. I would like to underline that the wavelength of the pulses used in this experiment is 800 nanometer, which means that the electric and magnetic field oscillating in this light wave were oscillating at the frequency of 10 to the 14 hertz, 3 orders of magnitude higher than the frequency of the magnons, which means that we can rule out the possibility of a resonant coupling of the magnetic field of light with the spins. So the magnetic field of light did not excite resonantly the magnons. Therefore, the electric field must have done the job. And this poses kind of a challenge, kind of a problem, because we all know that when you describe light matter interactions in terms of electric dipole approximation, the spin flip is a transition which is forbidden, because delta F should be 0. So before I can clearly explain why and how the electric field can excite magnons, I need to recall very quickly what stimulated Raman scattering is about. Suppose that you have a magnetic system in its ground state. This magnetic system can interact with a light beam at the frequency omega-1 in a non-resonant way. When this interaction occurs, the system is brought into a virtual state. From the virtual state, Raman emission can occur. A magnon or a phonon can be scattered, and the Stokes beam is emitted. The Stokes beam is emitted at frequency omega-1 minus omega capital M, where omega capital M is the frequency of the magnon. It's just a conventional spontaneous Raman scattering. However, you can stimulate this emission, you can stimulate this process if you send a second light beam at the frequency omega-2, with the condition that the frequency omega-2 must be equal to omega-1 minus omega capital M. In this case, you can basically combine spontaneous Raman and stimulated emission, and you get stimulated Raman scattering. The experiment that I've just shown you was done with femtosecond laser pulses, which by being ultra short are necessarily broadband, so broadband that the two frequencies, omega-1 and omega-2, are contained in a single laser pulse. This is nice, is what we call impulsive stimulated Raman scattering, ISRS, but this is not explaining yet how the electric field of light can flip spins. To do that, I will use a very old and elegant argument which comes from the review published by Florian Lodon. It's a stunning review about light scattering on magnons. And they assume to have a magnetic material with orbital angular momentum quenched in the ground state. This is not a strange requirement because in many systems, the geometry of the crystal field quenches the orbital momentum. As a consequence, the ground state can be split only by exchange. In the excited state, we assume to have some spin-orbit coupling, and we consider only the splitting due to spin-orbit coupling of these levels. In this situation, you can identify couples of electric dipole transitions, these arrows basically, which are totally allowed by the selection rules. But if you look carefully, the difference between the initial and the final state of these pairs of transition differs by a single unity of the Z component of the spin, which means that the difference between the initial and the final state is a spin flip. This basically means that it is indeed true. A single electric dipole transition cannot flip a spin, delta S 0. But a series of allowed electric dipole transition can flip spins and generate magnons, provided that the spin-orbit coupling is non-zero in the excited state, which is absolutely not a tight requirement. I am discussing light scattering on magnons, so Raman scattering on magnons. This is a very general concept, so we can formulate, in principle, a very simple Hamiltonian describing the light-matter interaction. So we use the dielectric tensor, which is a function of the spin, because the system is magnetic, and the electric field of light. So let's assume that our spins are along the z direction in the ground state. This means that the operators Sx and Sy represent spin deviations. So they're associated with the generation of magnons and spin flip. Now, the tensor epsilon can be expanded in a function of spin, and also this is a textbook procedure. And as you can see, we have several terms. I would like to state that this is done in non-dissipative approximation, so all these terms are fully real. Of course, non-dissipative approximation is the spirit of working with dielectrics. If you have dissipation, if you have absorption, you can also consider the complex part of the dielectric tensor, and you have more terms, basically. So the first term, as you can see, is linear in the spin deviation, so it represents a delta S equal 1 process, which means single spin flip generation of one magnon. The second term is a bit tricky. It is quadratic in the spin, but first of all, it's quadratic in the spin on the same ionic site, Si. Second, if you work out all the components of this tensor, you find out that if your material has decent symmetry, or very good, very high symmetry, the only configuration that you have, the only combination of the spin coordinates that you have is Sz times spin deviation. So this term, although it's quadratic overall in the spin, is linear in the spin deviation. And so it can describe only delta S equal 1 excitation. It's still a single Magnon excitation, but with different geometries and selection rules from this one because of the difference in the tensors. Even the order of the tensors is different. The last term is probably the most intriguing one, because as you can see, it's proportional in a quadratic way to the spin, but this time we have spins on different sublattices, Si and J, so also spins on different ionic sites. This means that you can in principle use this term to describe spin flip on different sublattices, so generation of multi-magnons, and this basically will be the focus of the second part of my talk. I would like now to focus your attention on a very general and important properties. I'm using the dielectric tensor to describe how light excites magnons. But the dielectric tensor, if you if you use it in the Maxwell equation, is used to describe how the properties of light are changed by the interaction of a material. So you take exactly the same terms, you put them in the Maxwell equation, and you can calculate how light is affected by propagation through a magnetic medium, which means that these tensors are all the magneto-optical effects. The first one is the Faraday rotation, Faraday effect. The second one is the magnetic inner fringes. And for each one of these terms, you can associate another magneto-optical effect. So the key point, and I would say the most important message here, is that magneto-optics and opto-magnetism, so excitation of magnons by light, have the same microscopic origin, which is Raman scattering on magnons. Since, again, I'm talking about Raman scattering, I'm talking about something super general. So general that has been demonstrated in a lot of materials with different magnetic structure, different electronic properties. And the common feature of all these experiments that have been reported is that the photon energy of the palm beam is below the band gap. However, this doesn't mean that there is absolutely no heating, because below the band gap you can have local absorption from the electrons. And actually, in all the experiments that I'm reporting here, some d electrons absorb light. So even if the heating is very small in comparison with a real interband transition above the band gap, is non-zero. And for this reason, this approach has been strongly criticized a couple of years ago, because the critic went like this. They said, okay, you always talk about light scattering, you always say that it's non-dissipative regime, but in any experiment, there is some absorption. Why? So this is the first big question that we faced a couple of years ago, and we wanted to understand if we can do optomagnetism without absorption. So we chose a sample that is it's really a nice sample for this purpose, and the sample is potassium nickel trifluoride. This system is a cubic Heisenberg antiferromagnet with exchange interaction only among nearest neighbors. The Néel temperature is rather high, 246 Kelvin, and this is really the idea of the Heisenberg antiferromagnet along the 3 cubic axes. So the Heisenberg chains along the 3 cubic axes. Very simple system. And for us, this is interesting because of the optical properties. The absorption spectrum, measured up to 5 electron volt, does not show the band gap. The band gap is at 6.2, so even higher. more interestingly for us is the optical region. In the optical regime, you have some DD transition, well addressed in the literature, which alternate to this transparency region at 2.2 electron volt. So our idea is really simple. We want to excite spin dynamics and study changing our photon excitation in this range to study the effect of absorption on the spin dynamics, and more specifically, to understand if it is possible to excite these coherent magnons without any absorption. So I will describe now very quickly how pump probe experiment works. We use basically two laser beams, a very strong one called the pump, which has the goal to excite dynamics in the system. Then we use a second laser beam, much weaker, the probe, which must not excite anything in the sample. The probe must simply detect the modification in the sample induced by the pump beam. So we recollect the probe and we analyze the polarization of the probe to understand what the pump induced in the sample. We analyze the polarization because we're interested in spin dynamics. So we want to measure magneto-optical effects induced by the pump beam. As you can see in the cartoon here, we do not measure modification of the rotation of the polarization, but the modification of the ellipticity. We did this because we wanted to measure magnetic linear birefringence. Before I explain you why we measure, I would like, of course, to explain you what magnetic linear birefringence is. Again, we have two systems, two collinear sublattices in our Heisenberg antiferromagnet, and we introduce the order parameter with the conventional definition. The magnetic linear birefringence is simply the difference in the refractive index along this direction and the direction orthogonal to the spins, nothing more. As I mentioned previously when I showed the expansion of the dielectric tensor, this effect is quadratic function of the spin. So you can write it as a function of the quadratic combination of the order parameter. Now, if you have an Heisenberg antiferromagnet and you excite dynamics, there are two different kinds of dynamics. You have transversal, spin dynamics, and longitudinal. Some of our colleagues try to measure dynamics in antiferromagnets looking at the transversal component. So what they did is measuring the transient magnetization. This was done by measuring Faraday rotation, and they could indeed measure some signal because in the transient state, there is some transient magnetization given by this expression. But if you want to measure longitudinal spin dynamics, this doesn't work because in the initial and in the final state, the magnetization is always zero. If the dynamics is longitudinal, the L dt is parallel to L, so there is no transient magnetization. If you want to measure it, you have to measure an effect like the transient magnetic linear birefringence, which has two contributions, one sensitive to the transversal component, and the second sensitive to the longitudinal component. Now, why do we have to bother to do this? Because we care about heating of the spins. If you hit a ferromagnet, the magnetization shrink. If you hit an antiferromagnet, the magnetization of both sublattices shrink. So if you want to discuss the effect of laser heating of spins, you must be able to probe the two components of spin dynamics simultaneously. That's what we did. The first experiment was done pumping at 1.5 electron volt, which means that we pump at the D transition. So we observe oscillations at the frequency of 90 gigahertz, which matches the frequency of the k equals 0 magnons in this material. And then we observe this second feature, this sort of background that we call here B. Measuring as a function of the temperature revealed that B decreases as the nil point is approached. So it seems to be a fingerprint of the magnetic system. We know that in principle we are sensitive to two contributions. So when we fitted our data, we ascribe the oscillation to the transversal components of spin dynamics and this background to the longitudinal component. We formulated a suggestion for a scenario to explain this, and the scenario is rather straightforward. So our pump beam excites coherent magnons via impulsive stimulated Raman scattering. At these magnons, the phase on a time scale determined by scattering events. When they dephase, this dissipation goes into heating of the spins. But at the same time, a fraction of the pump beam is absorbed because we pump at the D transition. These D electrons have no mobility. So there is nothing like a photo-induced current like in a semiconductor. So typically, this localized D electron decay in a non-radiative way in less than 1 picosecond, and they release energy to the lattice. Now the lattice is hot, and via phono-magnon scattering, it can contribute to heat flow to the spins. And this typically happens on a 100 picosecond time scale. This is just a suggestion, so we want to confirm this, and to confirm this, we change the photon energy of the pump beam. So first, we start to excite the highest transition that we can excite in our range, And we observed that the B signal, so this background, is the highest ever seen in our experiment. All the data are normalized on the incoming intensity of the laser, so you can directly compare them, basically. Then we moved to the smallest transition at 1.9 eV, and we observed that this background contribution is the minimum. This is consistent with what I've shown you moments ago. The bigger the absorption, the more you heat up the lattice, and the more, in the end, contribution you have of heating to your spin system. And this is expressed by a bigger components of this background signal. Now, the whole goal of doing this was, of course, studying the transparency region. When we did that, we expected to observe nice oscillations and nothing more. Indeed, we got nice oscillations, but we also got a small background. If you look at the scale, it's much smaller than in the other cases, but it's non-zero. It's there, always there. We can always measure, fully reproducible. So, to understand a little bit what is going on, as you can see, we fitted all our data. And now we would like to summarize basically what we learned from the fitting procedure. What we did was a comparison of this background feature, and as I've already discussed, the higher the absorption and the bigger this contribution is. And then we have two time scales in our system when we pump some transitions. We have a time scale of the damping of the oscillations, this one, and a time scale for the increasing of the background. They are different because they come from different, they represent different phenomena. The damping is simply given by scattering of these magnons with the environment, while the rising of this feature comes from phono-magnon scattering. But when we pump in transparency, we kill one of these channels of energy transfer, simply because there is no more absorption of light. So in this case, we generate still coherent magnons in the same exact way, impulsive stimulated Raman scattering, and there is still the phasing determined by scattering. But in this case, and only in this case, this dephasing is the only source of heating of spins. There is no fingerprints and no contribution from electrons and the lattice. If this suggestion is correct, this means that when we try to fit the data with this function, assuming two different time constants, we must find that the two time constants are equivalent. So we did it, and we found out that to the best of our experimental uncertainty, these two time constants are the same only in this case, when we pump in transparency. And this means that this regime of spin dynamics is significantly different because there is no contribution of the lattice and the spins. We can heat up the magnetic system only via the phasing of coherent magnons. So we call, for this reason, we call this regime zero absorption regime, exactly meaning that there is no contribution of phonons and electrons to the spin dynamics, but only contribution from the spins. We can also take the next step, let's say, and formulate a criterion that allows to state whether we are in this regime or not. And the criterion is simply the quality of the two time constants. If you measure with the same experimental procedure and you find this condition, you can be sure that you are in this regime. You are not hitting the spins with the lattice, but only by magnetic decoherence in the end. If you now consider the dynamics of this problem, so these oscillations and this heating up of the spins, you can as well do a simulation to basically describe this behavior using only classical equation of motion. You can write a system of Landau-Lifshitz equation with Hilbert damping, also block relaxation for the longitudinal components, but you can do it. In this paper, we did it using the nonlinear sigma model, which is in the end equivalent to Landau-Lifshitz. So in this sense, this regime of spin dynamics is fully classical. You can use classical equation of motion. In the beginning, I've said that the goal here is combining ultrafast, so femto, magnetism, spin, and nano. We would like to have an approach that you can scale down with the perspective of potential future devices. And this is not the way, because these oscillations are macroscopic, the wavelengths are micrometers and micrometers, so you have to do something different. So let's go back to square one, and let's take a look again at the dispersion of magnons. Our goal is again, femto plus nano plus spin. So it is natural for us to start to look near the edges of the Brillouin zone, because here magnons have femtosecond period and nanometer wavelength. Moreover, the energy of these magnons is mostly defined by the exchange interaction. That's why magnonics people call these magnons exchange magnons. I prefer to use the word femto-nanomagnons. And our strategy is absolutely clear and really straightforward. We want to measure the macroscopic spin dynamics induced by the generation of femto-nanomagnons. Now, this plan is crystal clear. However, it is hard to execute because there is no ultrafast stimulus that matches simultaneously the frequency and the wave vector of the femto-nanomagnons. However, sometimes it is possible to circumvent the problem, and I'm going to show you how. So let's consider our antiferromagnet, two sublattices. Of course, the total spin is 0, the total magnetization is 0. It's an antiferromagnet. Now, suppose that we can flip one spin per sublattice. If we flip one spin per sublattice, the total spin of each sublattice is decreased by a unity, and the antiferromagnetic vector is decreased as well. As you can see, in the final state, the total spin is still 0. The total magnetization is still 0. So this excitation is a delta S equals 0 process. Moreover, when you flip two spins in a magnetic material, you generate two magnons. This is unavoidable. All the spins are coupled by the exchange. If you flip one of them, you trigger a magnon. If these two magnons that you generate have the same and opposite wave vector, so equal and opposite wave vector, k minus k, this excitation can conserve also the wave vector. So if we have a delta S equals 0 and delta k equals 0 excitation, this means that looking at the conservation laws, a light beam can induce this state. This state is called two-magnon mode, and in principle, if you just look at the conservation laws, you can excite in this way any pairs of magnon throughout the dispersion. The only condition is that the two magnons have k minus k, same and opposite wave vector. However, if you look into this, you will realize that only magnons near the edges of the Brillouin zone are actually involved. And the reason is that the dispersion tends to flatten near the edges, so the density of state is here the maximum. So talking about magnons near the edges of the Brillouin zone, we shouldn't then be surprised by the fact that the energy of the two-magnon mode is basically the exchange energy. There is also a second term, delta, but this is a correction due to magnon-magnon interaction. The driving term is the exchange energy. Now, the concept of the two-magnon mode is not a novel concept, and it is based on the idea that flipping two spins in an antiferromagnet gives delta S equals 0. For this reason, such an excitation is impossible in a ferromagnet. If you take a ferromagnet and you flip two spins, you get delta S2 or minus 2, but for sure you never get 0. That's why this mode does not exist for a ferromagnet. And that's why, if you use a light beam, you cannot access the edges of the Brillouin zone in a ferromagnet. This is exactly the reason why, in the beginning, I said that if you use light to excite spin dynamics, you go dramatically faster in an antiferromagnet, exactly for this reason. This concept, as I said, is not new. Is in the end a concept that enters in the big literature of Raman scattering of magnons. I'm showing you now a very old Raman spectrum from potassium nickel trifluoride. This very broad mode is the two-magnon mode. You have a Raman active mode, and we want to study ultrafast spin dynamics. Here, if we look at the experimental technique, we have a choice. We can try to do time-resolved Raman spectroscopy, which we did. But if you do time-resolved Raman spectroscopy, you start to fight with limitation of the technique, fundamental limitation. There are theory papers that show that if you try to do time-resolved Raman spectroscopy, the signal that you see in the first picosecond is a convolution of real dynamics and, in the end, artifacts. And it's extremely challenging to disentangle these two contributions. So we understood that it is tough, and so we tried to do, again, an experiment of impulsive stimulated Raman scattering on the two-magnon mode. But this is much more difficult than the previous one, because the condition that the laser pulse is broad enough to have the two frequencies can be translated into the time domain. And in the time domain, it means that the duration of the laser pulse has to be shorter of the period of the mode that you want to excite. The period of the mode, since it's very high energy magnons, is 45 femtoseconds, so we need 10 femtosecond laser pulses. And believe me here, to get 100 femtoseconds is easy, it's commercial. Go down from 100 to 10 is something extremely challenging that only few labs are able to achieve. So the experimental geometry is absolutely equivalent to the previous one. The only difference is that this time we measure rotation of the polarization. I would like to point out that the detection cannot be based on linear magnetoptics. If you try to measure the Faraday rotation, you measure delta S equal 1 processes. You measure something linear in the spin deviation. But the two-magnon is generated, the two-magnon mode is generated by two spin flip. Delta S is 0. So you need a magnetoptical effect quadratic. But more specifically, you need a magnetoptical effect that is proportional to spins belonging to both sublattices. And in a nearest neighbor Heisenberg antiferromagnet, this means spins belonging to different ionic sites, Si, Sj. please notice that this correlation function is the same correlation function that appears in the Heisenberg term of the Hamiltonian. It's exactly the same. So, after all this introduction, finally I can show you the data. Our first experiments revealed oscillations at the frequency of 22 terahertz, so period of 45 femtoseconds, a lifetime of 500 femtoseconds. These numbers are in excellent agreement with the position and the bandwidth of the two Magnon mode observed in Raman spectroscopy on the same compound. Of course, this is not enough to claim and to conclude that we did excite and we did probe this mode. So we studied temperature dependence of the effect. What we observed is that the frequency and the lifetime of the mode decrease as the nil point is approached. Then we plot the temperature dependence of frequency and the bandwidth, the lifetime of these oscillations, and we compare them with a spontaneous Raman experiment that we did perform on the very same specimen. The striking agreement between these curves allow us to conclude that we did excite the two Magnon mode and we did probe it on the ultra-fast time scale. But if you think back for a moment to the dispersion, I've told you that this mode means looking at the edges of the Brillouin zone. So this means that the oscillation that you're looking at right now do correspond to coherent magnons with a frequency of 22 terahertz, a wavelength of 1 nanometer. This is fantastic for me, but now we would like to understand a little bit better what we're looking at. So we try to formulate a model based on an Hamiltonian with two terms. H0 is the usual Heisenberg exchange, and then we need an interaction term. So we chose something typical for a two Magnon scattering. In this term, you get a delta function that represents the laser pulse, some boring constants, and then you get the spin dependence. The spin dependence is, of course, quadratic. It's fully symmetric in the xy plane, and this can describe one spin flip per sublattice, so the delta S equals 0 process that we're interested in. When you have a full Hamiltonian, what you can do is solve the time-dependent Schrödinger equation, and when you have the time-dependent state, you can calculate expectation values. For us, it was interesting to calculate two very specific expectation values. First, the expectation value of the spin correlation function. We know that with magneto-optics we can measure this, and we actually did it. But we also would like to understand what this excitation means for the order parameter. So we excite these femtonanomagnons, but what does this mean for the antiferromagnetic vector? So we calculated the time dependence of the antiferromagnetic vector, summing the contribution from all spins and all sublattices. And what we found out, to my surprise at least, is that if you neglect Magnon-Magnon interaction at the leading order, these two quantities have the same time dependence. Therefore, we can now interpret the signal that we observed, these oscillations, as coherent longitudinal oscillation of the order parameter. And this means, basically, that our magneto-optical experiment, which is a macroscopic experimental technique, allowed us to track the femtosecond dynamics of the correlation between spins, and these spins are nearest neighbor. So these spins are 4 angstroms away in the unit cell. And we could access this with optics. No X-ray. It's a sub-wavelength experiment. Moreover, the model suggests that we can map these dynamics into the dynamics of the order parameter, but let me stress, we do this via modeling. We didn't measure directly the order parameter. I want to be clear on that. And on top of that, if you know that you measure the dynamics of the spin correlation function, you know that you're also measuring the dynamics of the exchange energy, by the way. This, in my opinion, is already quite some result, but our goal is to manipulate the macroscopic magnetic order on the femtosecond time scale. So we took this concept and we tried to bring it to the next level. First, we excite our sample with a single pump beam, and we observe the usual oscillations. Then we rotate the polarization of our pump beam, and we observe that the sign of the signal is reversed. So, okay, we have shown that we can manipulate the phase of these magnons, which is relevant, especially for people working in magnonics. But we would like also to be able to manipulate the amplitude of these magnons. We did this in a double pulse excitation scheme. So we have 2 pump pulses with a delay. When the delay is equal to the period of the two Magnon mode, the oscillations are enhanced. While when the delay is set equal to half the period of the two Magnon mode, the signal is suppressed. But this means that we did achieve a coherent manipulation of the macroscopic order parameter in an antiferromagnet on a 10 femtosecond time scale. We did this by exciting femtonanomagnons. So we open up the regime that we define femtonanomagnomics, and we are very excited by it. However, one paper, one work is not enough to exhaust the problem. So we are currently working on this, And I would like now to give you a small preview of what we are doing right now. What we would like to understand a bit better is exactly the nature of the dynamics of this regime that we excited. So we have the excitation. We want to understand better the spin dynamics that we excite, this oscillation. So we started recalling the potential. I've already told you this is a classical choice for this problem. It's been already employed in the literature. And this system, the dependence of the spin of this term is quadratic. But to be more specific, if you focus on this part, you can rewrite this as Sx plus Sy, which means that you have a problem symmetric in the xy plane. So that is the direction of the spins before we pump, and the light matter interaction is symmetric in the xy plane. This can maybe seem like a trivial observation, but it's actually very powerful, because the consequence is that any kind of macroscopic spin precession is forbidden. The only dynamics that you can have is longitudinal. And the reason is rather straightforward. If you have spins along the z direction and you want to start a precession, you have to select an x or y component to start the selection. And this means breaking the symmetry in the xy plane. This happens when in the energy you have a term linear in Sx or Sy, which couples to an external magnetic field or to the spin-orbit coupling. And you can have this precession. But this is not the case. This is the only interaction term that we have. So we understand from this simple observation that the spin dynamics is purely longitudinal. And this comes with a challenge. The challenge and the problem is that you cannot use any classical equation of motion. If you try to use any Landau-Lifshitz equation to describe this, then you have a problem, because these equations are all torque equations. If you have a torque, you have precession, and nothing of this happens here. So what we are trying to develop right now is a theoretical approach in which we can demonstrate in a rigorous way that this regime of spin dynamics is a purely quantum mechanical effect with no classical counterpart. Of course, we are perfectly aware of the fact that many of our colleagues really love working with phenomenology to describe the spin dynamics. So we are trying to develop at the same time a sort of artificial semi-classical approach in which we can describe with some equation of motion different from Landau-Lifshitz this particular regime of spin dynamics. As you can imagine, these two tasks are challenging, and it's something that only proper and real theoretician can do. And I feel like I'm blessed because I have the chance to work with two of the best of them. Okay, I don't need to introduce Ellen to you. But I would like to say that also Dr. Johan Mentik is an expert of magnetic system, especially magnetic system out of equilibrium. This is all about the theoretical investigation of the regime, but of course we need to pursue also an experimental investigation of the femtonics, and in particular I would like to focus on 2 points. First is the manipulation of the phase. The manipulation of the phase is important, especially for magnonics people. And we would like to understand why. If you take two materials with the same optical spectrum, the same magnetic structure, you can, in one case, manipulate the phase of the magnons, as I've shown you, and in the second case, you cannot. So we would like to formulate a sort of experimental protocol that states what you have to do in the lab to be able to manipulate the phase of these magnons. Second point is to understand the role of the nil point in the femtonanomagnonics. So the Raman literature here is very clear. The Raman literature states that you can observe the two Magnon mode also above the nil point. Because at the nil point you lose the long range order, but the short range correlations will survive. However, 10 years ago, 2 papers were published stating that this is not possible in the time domain. There were some measurements, there were some arguments involving contribution of long range order in the time domain signal. So we want to solve this issue, set the issues once for all. And as far as I can tell you right now, it really seems that the old Raman literature was perfectly right. As I've said, this is still work in progress, and I would like now to move to the conclusion of my talk. I've shown you that if you choose properly the pump photon energy, you can drive the pathway of heating of the spins in your system. And I've shown you that if you excite magnons near the edges of the Brillouin zone, you can look at dynamics of correlation between spins that are 4 angstroms away in the material on a 10th femtosecond time scale. These open up what we call femtonanomagnonics, this novel regime of spin dynamics. If you're interested in the femtonanomagnonics, or in general, you would like to know how you can excite spins on the ultrafast time scale and nanometer length scale simultaneously in different materials, metals, in different techniques, also with X-ray, then you are lucky, we have recently published an invited review which covers all the most recent and relevant results in this research direction. Nowadays, experimental physics is absolutely a team effort. I could have done nothing of this without the big contribution and collaboration of all the incredible people that I'm showing here. In particular, I would like to acknowledge Alexei Kimel, who was my PhD advisor, and he's definitely the world-leading scientist in ultrafast spin dynamics. Of course, I also would like to acknowledge the funding agency, in particular the Laser Lab Europe network, which supported part of the experimental activity when I was in Europe, and the JSPS Foundation, which awarded me the individual fellowship that I'm using right now in Japan. And of course, I thank you all very much for your attention.